Okay, good morning, everyone. Welcome to day 3 of the school. So we start with INFN's third lecture, right? About non-invertible symmetries. Fourth? Sorry, please.
All right. Good morning. Welcome back, everyone. So today will be the last lecture from me on non-invertible symmetries. So in the previous lectures, we have been focusing on the big picture, the general structure of non-invertible symmetries, and especially we spelled out a lot of this general structure in detail in two-dimensional CFTs. And in this lecture, we'll apply the knowledge we have gained to identifying non-invertible symmetry in the very simple CFT, just to get our hands dirty. That is in the case of this one of the standard first non-trivial CFT that you probably encounter in any CFT class, the Icing CFT in 2 dimensions. Okay. As I'll explain, this very simple CFT already gives an interesting instance of a non-invertible symmetry generated by a topological defect line. Okay. So let us start with a brief reminder about, well, a brief review of the CFT. Okay. So first of all, the CFT has a center charge equal to 1/2. Okay. So it's one of the simplest CFT, and the operator spectrum, equivalently the Hilbert space on S1, contain these primaries. Okay, with subscript denoting the scaling dimensions, the identity operator, the spring operator of dimension 1/16, 1/16, and the energy operator of dimension 1/2, 1/2. Okay, and together with, because we are talking about 2-dimensional CFT, the operator spectrum organized into Virasoro primaries and descendants. Here I'm listing the primaries, and then the rest of the states in the Hilbert space are generated by the Virasoro descendants. This CFT has a famous symmetry, a very simple symmetry. That is the Z2 splint flip symmetry. The symmetry acts on the CFT. This symmetry acts on the CFT in a very simple way. All of the operators in this Hilbert space, corresponding state in the Hilbert space, are even under the symmetry, except for the sigma operator and its Virasoro descendant. The sigma operator and their Virasoro descendants are odd under Z2 symmetry. And in terms of the notation that we have introduced, let's call this symmetry generated by a topological defect line eta. Okay. And in terms of the picture we have been drawing, this means that when eta acts on the local operator sigma, okay, by enclosing it, whenever we encounter this kind of graph in your correlation function, we're free to shrink this graph and obtain just the sigma operator, by the way, it's opposite sign at the same location. Okay. As I've told you in the very first lecture, a hallmark of symmetry is that it gives rise to selection rules. In particular, in this case, because sigma operator is odd, this implies immediately any correlation function that involves odd number of sigmas. In particular, the case with 3 sigmas inserted at arbitrary locations better be 0. But this CFT is very simple. It's so simple that you can actually compute all the correlation functions of these operators. I will not explain the technology, but you have to trust me that you can compute all the correlation functions. And then after you compute them, you will discover that, in fact, there's some other kind of hidden selection rule that says any correlation functions that involve an odd number of epsilon operators inserted at arbitrary points is again 0. Okay. So if you try to extrapolate from this picture down to here, you want to say that there may be some hidden selection rule that could be explained by some hidden symmetry. Okay, and that is the symmetry that we'll be identifying. It turns out that will be a non-invertible symmetry. Okay, just a historical remark. So there is non-invertible symmetry. The kind of the signal there, this non-invertible symmetry goes all the way back to Cramer's Vienna. Okay, there's some already suggestion of such a non-invertible symmetry in this simple model since the work of Cramer's and Vienna, I believe, in the 1930s. Okay. So back then, people studied a lattice version of the CFT. Okay. This is the last Icing lattice model. You can think about as the statistical model in two space dimensions, and it's described by a Hamiltonian normalized by the temperature in terms of nearest neighbor coupling of the spins on the square lattice. Imagine you have some square lattice, and on each side you have these spins known by SI, and they can take two values, plus minus 1. And this notation means that you introduce this kind of nearest neighbor coupling for each pair of nearest neighbors. Okay, and K is the dimensionless coupling constant. And as I said, as I was briefly saying, the same model. There's a very similar model related to this. That's described by one-dimensional transverse Icing model. That's the quantum version of this statistical model. This model is so simple that you can actually study its entire phase diagram as a function of K. Okay. And because we have observed the temperature over here, you see that this is equivalent to tune K is equivalent to tuning the temperature. So in particular, high temperature will correspond to the small k part of the phase diagram, and low temperature will correspond to large K. And in these limits, it's very simple to solve the model. Okay, I will not solve it here, but you find that high temperature, you have some non-degenerate vacua. Okay, and on the other hand, you have at low temperature, you have a doubly degenerate vacuum that correspond to spontaneous breaking of the Z2 spin flip. Okay. As a consequence, you expect there to be a phase transition between these two different phases. This is usually referred to as the disorder phase. This is referred to as order phase because the spontaneity symmetry breaking. Okay. There's some phase transition over here, which happens at a special value of K, which is denoted by Kc. That's a critical C, a critical value of K. And over here, the description is given by, there's a second order phase transition, and the phase transition is described by the Icing CFT. Which is the CFT we reviewed over here. Okay. In particular, the sigma operator, the spin operator, is the CFT version of this individual spins that live on the individual lattice sites. Okay. What is the statement of the Cramer's-Vienna duality? The Cramer's-Vienna found when they studied this Icing model, okay, as a function of K, there's some mysterious duality between the high temperature and the low temperature phase of the theory. They find what is the duality? They find the following equivalence relation, okay, that under the identification between a dual coupling, which I call K dual, this mysterious relation, okay, Icing, and you already see that if one is small, the other is large, and correspondingly, this relates, the duality relates to the low temperature and high temperature limit of this phase diagram. Okay. And in more detail, it was found out that the precise statement is that Icing at the low temperature is equivalent or is dual to Icing at high temperature, okay, in the infinite volume. But to be precise, you also need to introduce another Z2 gauge field. The reason being that if you don't worry about the global issue, if you care about the global issue in particular, like the number of degenerate ground states, obviously these two phases will not match. Okay, but introducing this additional Z2 gauge field, which gauges the Icing Z2 symmetry over here, fixes the problem so that it's actually an exact duality. And because this duality relates the low temperature and high temperature Icing model, and I should also say that in terms of the CFT, this phase diagram can be captured by the CFT, the Icing CFT, couples to a relevant deformation, well, deformed by a relevant deformation, figured by the precisely this energy operator, okay, which essentially dual to the Hamiltonian over here. Where m squared is the coupling. And translated into this phase diagram, this point corresponds to m squared equal to 0. So we are at the fixed point. And the high temperature phase corresponds to m squared bigger than 0. And the low temperature phase corresponds to m squared smaller than 0 in my convention. Okay. So you may have different convention for your definition of the action, and there could be opposite. These two phases could be flipped. Okay, but this is my definition. In any case, this duality can be written more explicitly as a transformation on this couplings from m squared going to minus m squared, okay, because it goes from low temperature to high temperature and vice versa. And correspondingly, because how it couples to the operator epsilon in your Icing CFT, this is equivalent to sending epsilon to minus epsilon. Okay, so this is already some hint that the Kramers-Weiney duality may be related to this hidden symmetry that explains the selection rule at the fixed point. Well, the duality relation doesn't end here. There's also the famous duality relation that relates the sigma operator to the mu operator. Okay, so recall sigma is the order operator. Okay, it corresponds to this spinning degrees freedom on the lattice. When it takes a non-trivial expectation value, that corresponds to the spontaneous symmetry breaking phase of the Icing model. Okay. On the other side, this is the disordered spin operator. Okay. This is the operator that takes VEV on the disordered phase or high temperature phase of the Icing model. Okay. So when I draw this diagram, okay, this is in terms of this order parameter sigma. All right. Then at the critical point, which in this case coincides with the self-dual point of this relation, meaning that Finch to Kc is equal to 1. This duality implies that the Icing CFT is equivalent to its Z2 orbital field. So this operation of coupling a quantum field theory to Z2 gauge field is essentially implementing the Z2 orbital field. Okay. And as is common for dualities, duality typically relates two descriptions of the same system. And if there's some parameter you can tune, then typically what happens is at a special point at the parameter where the duality becomes a self-duality, the self-duality can be described by a symmetry. For example, you see this happens a lot on the moduli space conformal manifold of two-dimensional CFTs. Okay? One prototypical example is the T-duality of a compact boson. Okay? T-duality maps the compact boson radius R to 2 over R. Okay, in certain units. That is not a symmetry in general. But at the self-dual radius, which is described as SU2 level 1, the T-duality becomes a very special Z2 symmetry in the SU2 level 1 WZW model. Okay, so we're expecting something similar here, and we will discover that is indeed the case. But the difference is that in the case of SU2 level 1, from the compact boson has special radius, that symmetry is invertible. Here we'll discover the corresponding symmetry will be non-invertible, okay, which is correlated with this very special feature. So this is a question we want to ask. Okay. So there's many ways to pin down what this symmetry is. Okay. So let me give you one argument that uses this very simple picture that we draw many times. That is the modular invariance. For different perspectives, you can two different perspectives you can adopt to view the torus Pareto function twisted by insertion of some putative topological defect line. Okay, so this is again the object we were considering is simply the torus Pareto function of this CFT twisted by this topological line. Okay, so right now we are not assuming what this topological line is. We're agnostic about the details of a line, but we'll deduce constraints from this very simple equation. Okay, and once again, this is the same object, but with the topological line oriented in a different way. Sorry, the other way around. Okay, and as we said before, this equality leads to this following relation between a Pareto function that's twisted in the time direction by the line defect insertion, weighted by the Hamiltonian associated with the CFT generated by L0 and L0 bar. And other hand, we have the trace with no other temporal insertion of the Hilbert space twisted by the insertion of the topological line. And the S-dual version of the torus modulus enter into this expression. Okay, so I'm writing this for general C, but here C is equal to 1/2 in this specific example. And the fact that the topological line preserves the stress tensor means that both left-hand side and right-hand side will have decompositions into the basic building block of 2D CFT, representation theory building block of 2D CFT, namely characters of the Russell algebra standard chart equal to 1/2. That is very constraining because unitary representations of the Russell algebra as at standard chart equal to 1/2 only comes in 3 families. Okay, they're in one-to-one correspondence with the operators that we are talking about in the Icing model in the absence of any additional insertion. Okay, the chiral representation. So that means the left-hand side is let me call it is a linear combination of the character associated with the identity operator. Okay, let me call it alpha1. Okay, alpha0. Sorry, and the coefficient multiplying the character associated with the 1/16 representation. Okay, and the character associated with the the h equal to 1/2 representation. Okay, and they correspond to physically the 3 operators: identity, sigma, and epsilon, as well as their descendants. And these coefficients, which we are being agnostic about, determines how this operator acts on this putative line operators acts on those operators. Okay, the line operator acts on those local operators. Okay, there are too many words about operators. Hopefully, there's no confusion. And we can do the same thing for the right-hand side. Okay, but as we said before, the right-hand side, in some sense, is more constrained. So even though we are, because we are agnostic about the detail of the line, we don't know much about this defect Hilbert space. But just from the Virasoro symmetry, we know whatever this defect Hilbert space is, it must be built from this basic building blocks, which involve these curve representations with weight 0, 1/2, and 1/16. Okay, so you have potential. You have a sum over two numbers. Each of this number can take value in this set of three possible representations. Okay, and the summand involves this coefficient, which is a positive integer, non-negative integer, that counts for the degeneracy of the representation in the given twisted Hilbert space. And they're multiplied by these characters. Okay. And this very simple relation, okay, so you have this equality, this very simple relation with the constraint that this coefficient, a positive integer, is surprisingly strong. Okay, so I'll leave that as a homework, okay, to show that there are three independent solutions to this equation. Okay. Meaning that all the other solution will be generated by positive integer combination of the solution I will write down. Okay. The first solution is such that, let me write those three solutions. The first solution is when they are both equal to 1. Okay. The second solution is 1 minus 1 and 1. Okay. And the third solution is square root of 2, 0 minus square root of 2. Okay. The case when it's acting as 1 on any of the three operators, identity, sigma, and epsilon, means that this is nothing but the trivial line, the identity line. The second one acts non-trivially, trivially on everything except for the sigma operator, as well as the sentence, identifies this operation generated by this putative line as the Z2 flip symmetry, Z2 spin flip symmetry. Okay, so this corresponds to the identity line. This corresponds to this eta line. Okay, and this is the object that will give rise to this duality defect. Okay, so this is the only other possibility. And as you'll see, this is indeed a consistent solution, a consistent symmetry operation. Okay, in the sense that we'll give an alternative description, a derivation of this result that does not rely on any assumption. Okay. But here it's like we assume the line exists. This is the most general form it can take. We'll give an alternate argument such that this line must exist. Okay. Question? Yes.
But is it okay that some coefficient is negative?
So these coefficients appear on the left-hand side. Okay. What's important? What's the equation? What's non-trivial about the equation is that these coefficients are always non-negative. So it's your homework to see that having certain coefficients being negative is fine. But for example, you cannot have this coefficient being negative.
But because in the left-hand side is not a partition function, it's a.
That's right. It's not a partition function.
Okay.
It's twisted in a temporal direction.
Okay.
Okay. So this left-hand side, keep track of how symmetry acts on the Hilbert space with no twist.
And sorry, and what are the corresponding value of the coefficient n? You are keeping it arbitrary.
Sorry, come again.
The coefficient nij are arbitrary.
Arbitrary, totally arbitrary. So but so to solve this equation, all you need to know is that this coefficient has this property, but you leave it general, and you will find the solutions will be in general a positive integer linear combination. Sorry, non-negative integer combinations of these guys.
But once you fix the alphas, the n going to be fixed.
Yeah, so once you fix alpha, the n is obviously fixed. But to determine alpha, you don't need to make assumptions on n apart from what I have said.
And sorry, just one other clarification. Why in the left-hand side you are assuming that this is diagonal?
Right. So this is what we know from something we just erased. Right. So so we know that the way this topological defect line act on the operators will be such that it cannot change its scaling dimension. In particular, it maps Virasoro multiplet to a Virasoro multiplet. In the Icing model, there's no degeneracy in the Hilbert space without twist, right? So for a given Virasoro representation, there's only one operator. So there's no other possibility than having just an overall number. Okay. All right. Okay. And we can learn a bit more from just this very simple table. Okay. Just from this how it acts on the operators in the untwisted Hilbert space, you can already infer the fusion rule. Okay. Okay. In particular, the fusion rule of obviously of eta squares identity. That's what we expect for a Z2 symmetry. Moreover, when you fuse the duality defect with eta in either way, you will recover the duality defect. Okay, that is because this entry is 0. Okay. Furthermore, if you square the duality defect, you get 1 plus eta. Okay. So these rules are uniquely determined just by postulating the most general fusion rule with non-negative fusion coefficients and consistency with this table. Okay. This defines what's known as the Icing fusion rule. Name is not so surprising. Okay. And as I said before, once you have a set of topological defect lines and you have specified the fusion rules, okay, there's the consistency condition just coming from locality of the theory says that they should furnish to this whole fusion category structure, meaning that it should have consistent solutions to the F symbols. So there's a consequence of locality and essentially the isotopy invariance. Okay. In other words, the F symbols associated with junctions formed by these topological defect lines would have to satisfy the Pentagon equation, and that has been solved. Okay, so here I'm listing the solutions. This problem was solved in generality that generalized this particular fusion rule in the case when the Z2 is replaced by a Zn by the work of Tambara and Yamagami. Okay, so in general, we call it Tambara-Yamagami fusion category associated with the general abelian symmetry. Okay, they generalize the case with just eta. Okay, but here I'm listing the full data of the fusion category in the case of this particular Icing fusion rule. Okay, so in particular, your simple objects are these 3 topological defect lines. They satisfy this fusion rule, which I showed before. And there's only one non-trivial junction where none of the 3 lines involve identity. So whenever 3 of the external legs involve identity that correspond to a trivial junction, okay, as we said before, that comes from just bringing the identity operator in the bulk to the defect line. Okay, this is the only non-trivial junction in this game. Okay, and then these non-trivial junctions enter into various non-trivial F symbol associated with this fusion category, which I have listed here. So the important thing is about this sign, okay, which is similar to what appears in the case of group-like symmetry case. Okay, the fusion symbols, the F symbols are faces in general, but the characteristic of this non-invertible symmetry case is that the F symbols are in general not just faces. It will involve this matrix elements, okay, which are not faces. Okay. And you will use.
Question?
There's a question.
Sorry, but we know that Tambara-Yamagami's fusion categories are not uniquely fixed by diffusion rules.
Very good, very good. So, so here I jumped over one small subtlety, is that if you just use this particular fusion rule for the Z2 case, there are two solutions up to gauge freedom to the F symbols. Here, what I'm writing down is the F symbol that will be relevant for the Icing CFT. Okay.
And there is some physical meaning to the choice of.
Sorry.
There is also some physical meaning for the choice of this one of the two solutions.
It's because the CFT actually realized just one of them. Icing CFT realized one of them. The other is realized by the SU2 W2W model at level 2.
And there is a way to see that.
That's right.
Okay.
That's right. Yes. But I'm afraid I don't have time to explain that detail here. Okay. But thanks for the question. Okay. And just from how this solution looked like, okay, it tells you how this duality defect acts on the untwisted Hilbert space. We have these diagrams, okay, which we have been drawing before. So acting on identity, which is equivalent to inserting nothing, okay, this gives you square root 2. Okay, we're just copying down the table over there into the diagram we have been drawing. Okay, this means that whenever you have this duality defect encircling nothing, you can just shrink it, and the cost is to include additional factor of square root 2. Okay. And if you have instead the epsilon operator inserted in the interior of this loop generated by the duality defect, you have the cost of introducing an extra minus sign. Okay. And similarly, instead, if you have the sigma operator inserted inside the loop, you will just have 0. Okay, it's completely annihilated. And this is the signature. This is another signature of this topological defect line being non-invertible. So it annihilates certain operators. Okay, but there will be in a sense where this operator will be recovered. Okay, but it will be recovered in a way that will be consistent with this duality relation. And this is what we'll see next. Okay, so instead of, as we said before, a feature of this non-invertible topological defect is that it doesn't just give maps between the Hilbert space twisted to itself. Okay, it also gives maps between defect Hilbert space twisted by a given line to a defect Hilbert space twisted by a different line. Okay, in particular, gives maps from the defect Hilbert space without twist to a defect Hilbert space with twist. Okay, and such linear operations are represented by, again, this kind of diagram. So this is a diagram that we call lasso diagram. Okay, when we discuss the generality, but potentially with a non-trivial junction. So I'll be using the red to represent eta, and using the, okay, this is not very red. The red line to represent this eta symmetry defect, and the white circle to represent the duality defect. Oh, I should also have said that here the defects that's involved in the Icing fusion category, they're all self-dual. So I do not need to keep track of the arrow. Okay, just in case you worry about this subtlety. Question?
Again, about the F symbols, is it not true that you always have the solution with trivial F symbols?
Come again?
Is it not true that you always have a solution with trivial F symbols?
No.
No? Okay.
No. So as I said before, F symbol, what F symbol is doing is giving you the change of basis between different representations of the junctions associated with 4 external legs. Because it's a change of basis, it will always have to be invertible. So it cannot be trivial.
By trivial,
identity?
Yeah, I don't mean 0. I mean that essentially you have no anomaly.
Yeah, so well, trivial. So trivial could be 0, trivial could be 1, identity matrix.
Yeah, 1. Let's say 1.
Yeah. So that would not be consistent because you have multiple fusion channels. Okay, that will be okay for when that's the case for non-anonymous group-like symmetry. But because you have these multiple channels, you cannot put 1 here and here. Okay, to be consistent.
So for some fusion rules, you necessarily have anomalies.
Come again?
What you're saying is that for given the future rules, there are future rules that implies automatically that you have Toft anomalies.
I'm not sure I get your question. Maybe it's better to ask that again in the discussion.
Okay, good.
Yeah. Okay. So what I was saying here is just that there's this additional actions, linear actions of these topological defects, the duality defect represented by these white circles, acting operators, okay, and sending operators not to the Hilbert space without twist, but to a Hilbert space twist. In this particular case, twisted specifically by the eta line. Okay. So once again, because every junction is topological, so you can shrink this diagram. So this produces for you an operator that's attached to this eta line. Okay. And this is precisely the operator mu that's relevant here. How do we see that? Okay. So once again, because the theory is simple enough, you can actually specify the entire Hilbert space. Okay. So every state that lives in here is a state in the Hilbert space twisted by eta. Okay. So similarly to the Icing model without twist, here the Hilbert space is completely fixed. It consists of the operator that correspond to the remnant of the fermion before you Booleanize the size of dimension 1/2 on either side. Okay. And just one other operator of dimension 116, 116. Okay. And for the same reason as before, this topological operation of shrinking this diagram, encircling this operator, does not change its scaling dimension. And because there's a single operator of dimension 116, 116, it has to be proportional to this guy. And the coefficient can be fixed by asking this operator to have a normalized 2-point functions. Okay. And what you find is that the coefficient with that particular choice of normalization is square root 2. And similarly, okay, just to be consistent with such a duality operation, another thing that you may wonder if is this kind of diagram, this again a lasso diagram, but encircling instead the mu operator. Okay, so like this. So for this to be consistent, this better give you something similar to this. Okay, so it should be 0. Why is this 0? Okay, this is why I draw it over here. Okay, this minus sign is crucial. So look at this region. Apply that F move. Because this operator is scalar, you can freely rotate this red spoke all the way around. And because in the process of moving all the way around, it crosses this point once, at which you use this operation, it gives off a minus sign. It will say that would mean that this diagram is equivalent to minus times itself. That implies this diagram vanishes. Okay. And furthermore, a similar exercise to what we did over here tell you that if you have this diagram, color not. Okay. Again, shrink it. So what this diagram means is that it's a map induced by the topological defect line on the Hilbert space twisted by eta into the Hilbert space without twist. Okay. So because when you shrink it, there's no dangling line defect. Okay. So this better produces the state in the Hilbert space without twist. And what you find is that it's indeed you recover this operator, okay, the spin operator. Okay. So what we see from these diagrams is the following. If we just focus on how the duality defect acts restricted to the Hilbert space without twist, it looks invertible. So it looks non-invertible because it annihilates the operator. But somehow this non-invertibility is not this invertibility can be recovered once you realize there are other non-trivial maps that maps one defect Hilbert space to another. In particular, the Hilbert space without twist to the Hilbert space with twist. Okay. So there's a sense in this particular non-invertible symmetry that once you include once you take into account how the duality defect acts on all the defect Hilbert spaces, it is really invertible. Okay, so you are not losing information, and that is why it makes sense to talk about it as a as a remnant of the duality, Kramers-Wiener duality at the self-dual point. So there's the picture that is helpful to represent the way the duality defect acts on local operators is to instead imagine that you have the duality defect over here and some local operator inserted around it. Okay, this is the diagram we draw when we discuss the topological feature of these defect lines. And as we know, as we have drawn this many times, okay, you can deform the duality defect line as a consequence of topology invariance, isotopy invariance. These diagrams produce the same observable when you insert in correlation functions. But because of this diagram, okay, this implies, okay, and you apply the fusion rule over here. So this is the fusion rule here is important. So let me so you apply the fusion rule for these two corners, okay, you apply the F move for that two corners using that rule. What you find is 1 over square root 2 times this diagram, okay, plus attached to the eta line and then further attached to the duality line. Okay, and then you use what we have already discussed over here. Okay, so there's one diagram I didn't draw, which is the case when you have this line attached to the epsilon. I'll leave that exercise to convince yourself that this is 0, okay, from a similar argument. And this implies, combining with this fact, okay, that this is equivalent to flipping the sign of epsilon. Okay, so the cost to move across this energy operator, to move the duality defect across the epsilon operator, is to flip its sign. You can do a similar analysis, and this is okay. And this explains this selection rule. Okay, so we have achieved in explaining the selection rule using this symmetry. Okay, and the way you do that is to put a topological defect line at one end and move it all the way. You pick up all the faces, but you can also annihilate to the vacuum. So, and you get a contradiction if this is non-zero, and that's how you argue the selection rule. Similar exercise. In view of time, let me again leave as a homework. But doing the same procedure again, using this the F symbols we wrote over there, what you will find is precisely the expected relation that says that when you move the duality defect across the sigma operator, which is charged on the Z2, you will get instead the disorder operator, which lives in the Hilbert space twisted by the D2 line. Okay? This explains this duality mapping between sigma and I mu. Okay? And you can do it also inversely, move the mu across and you bring the sigma. Okay, so combining this picture, this explains the Kramers-Wiener duality at the self-dual point with this non-trivial transformation rule that sends this basic operator in the Icing CFT. Okay. To these operators, which naturally are local operators in the Icing CFT after Z2 orbital. Okay. So the mu operator is not a good operator. It's not a good local operator before you do the orbital because it is attached to a non-local line. Okay. But after you do the orbital, this becomes a local operator. And this operation explains in what sense this is a precise symmetry. Okay. All right, so let's now discuss. So that's the kind of explicit example of how non-invertible symmetry works in motion. Okay. Let's now, given this example, let's now deduce some consequences. Okay. So the main point here is that this symmetry, just like a Z2 symmetry, okay, we discussed it in the very simple CFT, like Icing CFT, but the structure of the symmetry is quite general. Okay, it shows up in various interesting systems, and it can be used to deduce non-trivial consequences, for example, on RG flows. Okay, so this is what we'll discuss now. The dynamical consequence for RG flows. Okay. So what is the general picture for RG flow? Okay. So you have some, we focus on the case when you have some quantum field theory for which we'll call TUV, which is the UV description for some potential RG flow. Okay. Can trigger some RG flow, for example, by some relevant deformation or by gauging. Okay. This will end up with a non-trivial IR phase in general, okay, if the theory is strongly coupled. And there are several possibilities for what the IR phase may look like. So possibility number one is trivially gapped. Meaning that there's a unique vacuum that's gapped, okay, only massive excitations above the vacuum. Possibility number two is vacuum degeneracy, or in other words, a gapped with multiple vacua, okay, but discrete, okay, because it's gapped. This corresponds to the case, for example, when you have some discrete symmetry that is spontaneously broken, okay, in two-dimensional context. And the third possibility is gapless. In other words, described by a non-trivial CFT. Okay, so these are the three general possibilities for an RG flow. Okay, so let's focus on the two-dimension case from now on. And for example, consider RG flow triggered by a CFT in two dimension, perturbed by a relevant operator. Okay. That's the meaning of being relevant, okay. And also scalar, so that we preserve the Lorentz symmetry. Okay, so symmetry that's preserved by RG flow generally leads to constraints on what the IR phase diagram may look like. Okay, and here we want to consider this non-invertible symmetry. So we first need to introduce in what sense is non-invertible symmetry preserved by RG flow of this form. A non-invertible symmetry that generated by a topological defect line called L is conserved if it is transparent to the deformation operator. We can move it across the operator without introducing any phase factor. Okay? That means it's transparent, just like how stress tensor is always transparent to topological defects. This ensures that the topological defect remains topological under this deformation. Okay, and then there's a very simple theorem. Okay, once we have defined what it means for a symmetry generated by a non-invertible topological defect to be preserved under RG, there's a very simple theorem we can state. The theorem, the very simple theorem, states the following. If a quantum field theory admits a topological defect line, L, okay, such that its VEV, okay, its quantum dimension, its VEV on the cylinder, is not integer, positive integer, okay, but preserved along RG, then the IR theory, the IR phase, cannot be trivially gapped. Okay, so the only possibility will be a non-trivial TQFT, which is described in multiple vacua, okay, or a gapless CFT. And this is a very simple theorem. There are refined statements that constrains how precisely the symmetry is spontaneously broken. Okay. So let me just quickly give you the argument for this theorem, which is very simple to prove. So the proof proceeds by contradiction. Essentially, the same steps that you will go through in solving that homework problem will lead to the proof of this statement. Okay, and the proof actually only uses something even simpler. Okay, so assume, because we're proving by contradiction, we assume the theory flows through a TQFT or a gapped phase with one vacuum state. Okay, meaning that there's only one operator of dimension 0, 0 in this TQFT. Okay, and while it preserves a topological defect L. So we can simply consider this again, this torus primary function, twisted by the topological defect in the time direction, in the temporal direction, and which is related by a modular S transformation to the configuration with topological defect line inserted in the twisting the spatial direction. Okay, but in this TQFT, we can compute the primary function very simply. On the left-hand side, we have a trace over the Hilbert space S1, okay, twisted by this insertion, okay, the same L had before. Because the TQFT, the Hamiltonian is trivial, you literally just get a trace. There's no non-trivial Q dependence, okay. And because there's only one state in this Hilbert space, okay, there's only one state in the D by R. This just gives you the number, and that's nothing but the VEV of this line operator. But using the right-hand side of this representation of this relation, on the right-hand side, instead, you have a trace over the defect Hilbert space that's punctured through by this defect line. Okay, and there's nothing inserted because there's no more twist, and it just corresponds to 1. Okay, and just because you have a Hilbert space, this has to be a non-negative integer. So we arrive at the contradiction to the assumption in the theorem. Thus, we have proved the theorem. Okay. Yes.
So if the number of states in the twisted sector is bigger than 1, no?
Yeah.
Would you still call it a trivially gapped phase, or?
So it could be that in the twisted sector, there are more than one state. But as long as there's only a trivial vacuum, a single state in the untwisted sector, I would still call it a trivial gap phase.
Okay. Okay.
So according to this definition.
Okay,
That's
yeah, no,
that's where that's the circumstance where the theorem applies. Yes. But it can be refined. Yes.
oh, okay, okay. So does this also apply to higher dimensions then, or
Yeah. So,
well,
the,
okay,
the very same argument. So actually, yeah, very good. So very same argument applies in higher dimension, and indeed that is how the higher dimensional version of this dynamical constraint, taking this form, have been derived. Okay.
Thanks.
But of course, in higher dimension, you have more choices for what you call a torus, depending on the choice of the space d-1 dimensional slice. Okay, so let me now use the other side, the other table that I wrote before, to apply this dynamical constraint to another less trivial example, okay, beyond Icing. What is the simplest next non-trivial CFT is the tricritical Icing CFT, okay? So let me just write over here. So example of an application of this theorem, okay? So here I've written down the operator content of the tricritical Icing CFT. This is the next minimum model of Symmetry 7/16. It has 6 Virasoro primaries, and because the theory is so simple, you can actually solve the entire. You can actually identify all the topological defect line in this theory, and there are 6 of them. Okay, the detail is not important. What is important? There are 2 distinguished subcategories. This is one called the Fibonacci category. It's also called Li category. It is generated by a single topological defect line W, and it has this very interesting fusion rule. It squares to not quite itself, but with an additional identity line also appears. Okay, and it's this line is also same as its dual. Okay, and the Icing category appears also in this tricritical Icing CFT, and this is correlated with the fact that similar to the Icing CFT, the tricritical Icing CFT also have the Kramers-1 near type duality. It's self-dual under Z2 gauging. Okay, but what's important about this particular subcategories generated by the topological defect line W and N is that this W and N, they have the common feature that their VEVs, okay, are non-integral. In particular, the quantum dimension of this duality defect line is square root 2. Okay. On the other hand, the quantum dimension associated with this W line, because they have to solve the same polynomial equation given by the fusion rule, you can find out is a golden ratio. Okay. And so if you have any RG flow that preserve the symmetries, and from the general theorem we just discussed, then it's guaranteed to land on a non-trivial IR phase. So we just have to go through the table to find out which operators, if there are, preserving these lines. Okay, and then as we said, preserving means that you have this line over here, and you can move it across without introducing any factor. Okay, so this is the equivalent to this diagram. Is equal to the VEV of the topological defect line multiplying this operator. Okay, so if you, in terms of this diagram, this will be the equivalence relation. So we just have to go through this table and look for operators phi when L is either the W line or the duality line that this equation is satisfied. And it's easy to spot that for the duality line, the relevant operator, so you're looking for H, because H equal to H bar, you're looking for operators which smaller than 1. The relevant operator will be this one. Okay, so this is the operator that preserve the duality defect. Okay, and if you look for operator that preserve this W line, okay, then the only option is the sigma prime operator that is relevant. So what this means is that the tricritical we have the immediate prediction that trapezoidal Icing deformed by sigma prime, okay, and deformed by epsilon prime, okay. In this case, we preserve the Fibonacci category, okay. In this case, we preserve the Icing category, okay. So they cannot be trivially gapped. So if gapped, there has to be non-trivial vacuum degeneracy, okay. And you can actually derive a stronger result, which I did not explain. So you can actually show the minimal number of degeneracy is 2. Okay, and here the minimal degeneracy from a similar argument is equal to 3. Okay. But note that there's no other symmetry for these deformations. There's no other symmetry if we don't know about this non-invertible symmetry. Having some degeneracy, typically you want to interpret as something being spontaneously broken that leads to this degeneracy. Okay, just like the Z2 degeneracy in the Icing case in the low temperature phase. But here, there's no, if you don't have this non-invertible symmetry, there's no other symmetry that's responsible for these degeneracies. Okay, instead, these degeneracies are enforced by non-invertible symmetries. Okay. In particular, this is a prediction, and one can go ahead and check if this is actually the case, given the trapezoidal Icing model. Okay. This RG flow is integrable, and you can check this statement. Okay. So if it's gap, indeed, which corresponds to one particular sign of deformation, indeed, you have 3 degenerate vacuum. Okay. This side is not integrable. But you can check numerically, and you will find out that indeed has a 2 degenerate vacuum. Okay. It turns out that for this deformation, there's another possibility. As I said, the general theorem rules out the possibility of having a single vacuum, a single gap vacuum. There's other possibility of being a non-trivial CFT saturating this symmetry, and that is the nothing but the Icing CFT. Okay, with the opposite sign of this deformation. So. Okay, so this is just a very simple application of the general theorem we derived, and this is similar theorem can be applied in higher dimension to deduce similar statements. I think I'm running out of time, so let me just summarize these lectures by listing some other aspects which I did not discuss, but you are free to ask me afterwards. So let me just summarize. So in these lectures, we spent a lot on the basics of non-invertible symmetries. And hopefully through these lectures, I'll convince you that they are as good as the usual symmetries. Okay. In particular, they give rise to selection rules and leads to constraints on RG flows. Okay, or IR phase diagram of some UV description. What I didn't discuss is that in this lectures, I focus on the bosonic theories and topological defects in the bosonic theories. There are extensions to the fermionic case, just like the extension of bosonic group-like symmetry to fermionic case, including the fermion parity. And that story can be tied together with what I discussed using the bosonization duality, okay, in 2 dimensions and higher. And as I just discussed, this non-invertible symmetry, similarly to usual symmetries, can undergo spontaneous symmetry breaking, okay, and it can be used to explain degeneracy of the vacuum. And something I also didn't discuss is that this non-invertible symmetry, if they're not anomalous, they can be gauged. Okay, so there's a precise way to gauge a non-anomalous, in some sense, non-anomalous non-invertible symmetries. And this is the way to produce other CFTs. Okay, starting from CFTs with non-invertible symmetries. Okay, and the list goes on. Essentially, the list contains all the nice things we like about usual symmetries. And it's a more general, it's a kind of a more general, richer framework. Okay. And lastly, let me just try to connect to the other lectures. The very nice lectures by the other lecturers at the school. Okay, just posing some questions for you to think about. Okay, the obvious question in relation to Laura's lectures is to look for this non-invertible symmetries, okay, in the context of a celestial CFT. Okay, and the potential applications of these non-invertible symmetries on constraining the S matrix of massless particles. And in relation to Matthias and Kevin's lectures, a puzzle, current puzzle is to understand these non-invertible symmetries in the context of ADS-CFT. Okay, and in relation to the notion of no global symmetry in quantum gravity. Okay, so in particular, in the context study this non-invertible symmetry in the context of the ADS3 dimensionless string, okay, which is a very nice explicit playground to discuss the non-invertible symmetry in the quantum gravity. In that case, describe some explicit string theory, which we will hear more from Matthias. And similarly, in higher dimensions, perhaps in the twisted holography. Higher dimension, the string theory in the bulk is much more complicated. Perhaps one can make some progress using the twisted holography. Okay, so that is the end of my lectures. But hopefully, this will not be the end of your journey in the world of non-invertible symmetries. So sorry for going over time. I'll take questions.
Let's start for students. Maybe let's wait one more minute since people are still coming back. Okay, I think we can start now. So, Matthias is there. Is the microphone okay? Okay, welcome back. So we now have the lecture by Matthias about strings in ADS3. Please.
Okay, well, thank you very much. So let me remind you where we got to last time. So we are describing the strings on ADS3 cross S3 cross T4. And so far, we've been trying to understand how you describe strings on ADS3, and we've concentrated so far on bosonic strings on ADS3. And the idea is that ADS3 is geometrically a group manifold corresponding to SL2R, except we have to be careful about the periodicity in T, which we will have to undo, and I'll come back to that. So ADS3 is really the universal covering group of SL2R. And that factor we can describe in terms of an SL2R Wessel-Witten model if we are in the situation where we have pure Lewis-Schwartz flux. So it's a Wessel-Witten model based on the Lie algebra SL2R. And as I explained to you, once you add the Wessel-Mino term, you get conserved currents. These conserved currents are defined by this expression. And there's a corresponding formula for the left moving version of those. And they give rise to an affine Kac-Moody algebra, which is this infinite dimensional Lie algebra that I wrote down. And that's characterized by level K. And then the idea was that instead of trying to describe all classical solutions, given the fact that this theory has this enormous symmetry, we can use this as a way of organizing the space of states of this theory. And we argued that it should be given the Hilbert space. Well, Hilbert space is the wrong word because it's definitely not a Hilbert space. It has a it's not positive definite. It's the infinite dimensional vector space of physical excitations. And it has to organize itself in terms of representations of this affine Kac-Moody algebra, the left moving version and the right moving version. And therefore, schematically, it should be of the form that you have some representation on the left and some representation on the right. And initially, you would naively expect that these representations will be highest rate representations. And what I mean by a highest rate representation is that its Fock space is generated by terms of the form negative modes acting on some ground states. And the ground states are annihilated by the positive modes. So these are conventional highest rate representations. So they're killed by the positive modes, and the negative modes freely generate some Fock space. And normally you would expect your spectrum just to be described by highest rate representations on the left and highest rate representations on the right. And then the question is, what should this sum over J run over? And what this sum over J labels are these highest rate states. And what I mean by that is that we have an action of the zero modes of SL2R on these highest rate states. And specifically, I choose the conventions that the plus mode just shifts. You have obviously seen bracket JM before, if you know the representation theory of SU2. So J will stand for the spin, and M will stand for the magnetic quantum number. So J30 on JM will be just M. And J plus will move you up one step, and then J minus will move you down one step. And in these conventions, obviously sometimes you write this funny square root bracket factor here. I've decided to rescale my states so as to absorb this square root factor, and then it bites you here. There'll be a factor here, and the factor that appears here then is M into M minus 1 minus the Casimir applied to JM. And what is the Casimir? The Casimir operator is the generator JA0, JA0. And if you write it out in terms of this plus minus the generators, it'll be of the form a half times J plus 0, J minus 0, plus J minus 0, J plus 0, minus a half times J30, J30. So just like for SU2, what you show is that this combination of generators commutes with all the zero modes. So it's what's called a Casimir operator. Therefore, it takes a definite value in each irreducible representation. And what you take the value of this to be in the conventions. And so all of these things look like SU2, except there is a random number of minus signs scattered throughout. So for SU2, there would be a plus sign here. For SL2R, there's a minus sign here. For SU2, this would be J into J plus 1. And for SL2R, it's minus J into J minus 1. So there's always a 50% chance that a plus sign turns into a minus sign. Well, actually, judging by that, it's bigger than 50% because there are more minus signs than plus signs here. But that's, okay, you have to work a little bit to fix these signs, but it's basically SU2 with some some small bells and whistles giving rise to signs. So then the question is, what is the so what are the values of m that runs? Oh, I mean, when I specify j, what I mean by that, I specify the representation. The representation will be given by specifying what value j takes, and therefore what value the Casimir takes. That specifies the action of the zero modes then uniquely. And then I have to specify which values of m mod integer will appear, because the generators move the values of m up and down by integers. So I was mumbling words like Peter-Weyl theorem. So if you look at the situation where k is large, you can think about this geometrically. And then you can ask, what is the L2 space of SL2R? And it's described in terms of tensor products of representations of the finite dimensional group, i.e. SL2R. And then the logic is that in the quantum theory, in the string theory, you should sum over the same set of representations. So what are these representations? For the case of SL2R, what you should, there are two classes of representations that are so-called discrete representations. And they're characterized by j being a real number. And then m minus j must be an integer. In fact, m minus j must be positive, or the discrete representations of this kind. There's another family of discrete representations, but I'll just look at those. And in fact, in order for this theory to satisfy the no-ghost theorem, that is, once you impose the physical state condition, you end up with a positive definite space of states. You have to restrict this j parameter to a finite range. Namely, it has to satisfy that it's bigger than a half. Well, bigger than a half is sort of that goes for free, because this is a quadratic relation. So for a given value of Casimir, you can always choose, if it's real, you can always choose j to be bigger than a half. So it's bigger than a half, but then the no-ghost theorem tells you that it also has to be less than k plus 1 over 2. But you see, in the k goes to infinity limit, you don't care. And this is the analog of what you know for SU2. For SU2, the spin runs from a half to k over 2. So this is just the sort of SL2 analog of that. So these are the discrete representations. So here I have to sum over all of them. But you see, this is now an integral because j is real, j is not quantized because SL2R is non-compact. And therefore, you integrate over all the j's that run in this range. So this is really some sort of integral or integral sum. And then the second class of representations are the continuous representations. And these will be the real heroes in our story. So we will treat this a little bit, we will sweep them under the carpet. And I'll give you an explanation for why we're allowed to do this later on. Today, we'll just pretend that they don't exist. But we'll come to that later. And the continuous representations are characterized by the spin formally, the spin taking the value a half plus IP. And then if you plug this into the Casimir, what this tells you is that the Casimir is a quarter plus p squared, where p is a real number. And then, you see, I mean, this condition guarantees, if you stare at this formula, that j minus 0 on the state jj is equal to 0. So what these discrete representations look like is they have a state here where m is equal to j, and then j plus acts freely, and j minus stops here. So it basically looks like an infinite line, and you have a j plus a 0 going to the right, and you have j minus going to the left. So you increase the eigenvalue of m with j plus, and you decrease it with j minus, but there is a place where it stops. Namely, when m is equal to j, this prefactor goes equal to 0. And you see, this is sort of like the SU2 representations you're familiar with, except for the SU2 representation, you would look at this range, and here you look at this range. So it's basically, that's what it is. And for SU2, you would choose j to be half integer, whereas here we choose j to be any number, and we just look at what happens to the right. Whereas the continuous representations, so they are sort of semi-infinite, right? They run to the left ad infinitum, they never stop, but they stop to the right. There is the smallest value of m, but there's not the largest value of m. And then the continuous representations, they are unbounded in both directions. They run all the way, because you see, once C is of the form of a quarter plus P squared, or rather when J is equal to a half plus IP, since M is equal to real, this prefactor can never become 0. So therefore, this sort of a row of J minus operators and J plus operators will never stop. You will go as far to the left as you can go to the right. So this extends infinitely in both directions. And then because it never stops, there aren't any preferred values for M. So then M can really take any value. So the way you say is that M is in the set Z plus alpha. So these continuous representations are actually labeled by 2 parameters. They're labeled by the spin, which in this language corresponds to the real parameter P. And they're labeled by this parameter alpha, which tells you the quantization condition of M mod integer. And remember, I told you that the folklore is that strings on ADS3 can't, at the pure Navier-Schwarz background, which is what I'm describing here, can't be dual to the symmetric orbifold. And the reason I gave was that they have this continuum coming from the long strings out at infinity. And this continuum is exactly this continuum. So this P parameter is basically the momentum out at infinity. And the fact that this is continuous means there is really a continuous spectrum here, even after you impose the physical state condition. And therefore, this looks totally different than your symmetric orbifold theory, which has a discrete spectrum. So that's the folklore. And obviously, we will have to break the folklore in order to identify the worldsheet theory that's exactly due to the symmetric orbifold, because the symmetric orbifold, I mean, on the face of it, it has no chance to match any of these theories. Okay, so this is what you would naively expect, but that's not quite the right answer. And it's not quite the right answer for reasons that has to do with the fact that we're really interested in the universal cover of SL2R rather than the group manifold SL2R itself. Namely, what this part of the spectrum describes, if you think about it in terms of solutions, I mean, so you can ask what are the equations of motions that are, I mean, there's a sort of 2 dictionaries here. You can either write down the Wessel-Witten model, and you can look at the classical equations of motion on G. And what you find is the solutions for G are functions of the form sigma and tau that you can write as functions of G plus of X plus times G minus of X minus. This is the family of solutions of the Wessel-Witten model equations of motions. Right, so you could try to start with this and then quantize the phase space produced by all of these solutions. Now here we've sort of gone down a different route. We've said, okay, we know that this theory has this symmetry, and therefore we know that this space must organize itself in terms of representations of the affine Kac-Moody algebra. So you can ask, how does this language translate into writing down this Fock space of physical states? And the logic is that the states that are described by this Fock space correspond to those maps that have the property that G plus of X plus plus 2 pi. Remember, X plus and X minus are tau plus or minus sigma. So these are the worldsheet light current coordinate. And it obviously has to be, the worldsheet has to be periodic in sigma goes to sigma to 2 pi. So therefore, this function has to be periodic in sigma when sigma goes to sigma plus 2 pi. And how do you arrange for that? Well, you arrange for that by saying that G plus of X plus goes to, under rotation by 2 pi, goes to G plus of X plus times some fixed matrix, and G minus of X minus minus 2 pi goes to M to the minus 1 to G minus of X minus. Then obviously the product will be periodic, because you see this M will kill this M to the minus 1 when I multiply them together. So this will describe periodic solutions. And there is this sort of mental dictionary that the matrix here is fixed up to an element, up to conjugation. So it lives in the Cartan torus, and the different values of J, you can effectively think of describing the different matrices here. So roughly speaking, I don't want to explain this in detail, but the way you should think about it, the different values of J describe the different monodromies this solution describes, but they all describe strictly periodic solutions for SL2R. Because this is like the analog of what you do for SU2, and for SU2 there is nothing else. But for SL2, there is something else. So this doesn't account for all the interesting solutions because the T parameter here is not periodic in 2 pi. I mean, when you write it as a matrix in SL2R, it appears to be periodic in 2 pi, but it shouldn't be periodic because we want to look at this covering space, and therefore we have to include additional solutions. And the additional solutions we have to include they are of the form that you. So suppose you have a solution of this kind. I'm going to engineer a new solution that will account for the fact that T is not periodic. So what I do is I define G left of WR of X plus to be given of the form of e to the I times WR over 2. You'll see in a second why this is a smart thing to do. X plus times sigma 2 times G, what I call G0 left of X plus. So this is a solution of this kind. So let's call them G0 here. These are, and they satisfy this sort of periodicity where M is a fixed matrix in SL2R. And now the new solutions, I take an old solution of this kind and I multiply G left WR by this factor and G right of sorry, this should probably, this is actually an R. And then this is an L of X minus. What you do there is you multiply it from the other side. So I should have called this right. So this is left X minus, and then I multiply e to the I WL over 2 X minus times sigma 2. So, okay, so what I'm claiming is, suppose you have a solution of that kind. I propose, let's look at the solution that comes from this function for G plus and this function for G minus. What's the difference? Well, the difference, it's not as a monkey can see the difference, is obviously the factors of e to the I times something over there. But now remember, and that's the reason why I wrote out these equations over here, how we parameterized the group manifold to start with. So you see, on the left, we have e to the u times sigma 2, and on the right, we have e to the v times sigma 2. And the way I'm modifying these solutions is by multiplying them on the left by, I must admit, this is the world's most stupid convention to call the thing that stands on the left right and the thing that stands on the right left. And as you see, I've confused myself. But so this is acting on the left and this is acting on the right, despite appearances. So what this means is I take a solution, and relative to the solution I have before, what I do is, because of this factor, you see, this will effectively shift u as a function of X plus. So u will go to u goes to u plus WR over 2. You see, it's sigma 2, so it's WR over 2 times tau plus sigma. And it will shift v, which is the factor standing on the right here. You see, this is the v. So v is what stands on the right, and u is what stands on the left. So u gets shifted by this factor, and v gets shifted by the corresponding factor, WL over 2 times tau minus sigma. And now, why is this a smart thing to do? Well, remember that u and v are the light cone coordinates in target space. So if I translate them back into t and phi, t is the sum and phi is the difference. So what this means is that t gets shifted by t plus the sum. So there will be a term proportional to tau, which will go like a half times w right plus w left. And there will be a term proportional to sigma times a half times w right minus w left. And then phi gets shifted by phi plus tau times a half. And now I have to take the difference. So here there will be w right minus w left. And here there will be a half times w right plus w left. Okay, so suppose I have a solution that's described by this G0. And once I modify it in this way, I get a solution whose t and phi dependence, I mean, previously it was periodic, and now it picks up these additional pieces. And now, why is this interesting? You see, we want T not to be periodic. So we have to make sure that this factor is equal to 0, right? Because when sigma goes to sigma plus 2 pi, that must describe the same point. And in order to avoid T being periodically identified, I have to make sure that this factor is equal to 0. So this tells me I have to choose WR is equal to WL. So when I do this, then this term goes, and this term goes. And what I see here, this just becomes WR equals to W left equals to W. So what I find is T goes to T plus W times tau. Who cares? Tau is not periodic, T is not periodic. And phi goes to phi plus W times sigma, and sigma is 2 pi periodic, and phi is 2 pi periodic. So therefore, I've included now solutions that are not periodic in T, even if I go around with sigma by 2 pi. So I've made solutions that were periodic in T into solutions that are not periodic in T. And what I see is, it's not obvious that this accounts for all the possible things, but you at least see that you are producing arbitrary winding in the phi direction. And but you've undone the fact that this would have identified also the T direction. Okay, so that's the proposal of Maldacena and Oguri, was that what you have to do is you have to look at the solutions corresponding to this. But now I've translated it in terms of classical solutions. So in terms of classical solution, I also have to include these new solutions. But because I want to work in that language, I now have to explain what does this modification do on the level of the representations I've written over there.
Sorry, the winding in phi does have to be integer, so like W is an integer, or it can be.
Oh yeah, sorry, W has to be an integer. Absolutely. Sorry, I forgot to say it. Yes, absolutely. So W has to be an integer. Otherwise, I would. Yeah. Thank you. So here I've explained to you on the level of the classical solutions what I have to do. But I'm an algebraic CFT type person. I want to work in that language. So now I have to translate this description into this language. So what I have to do is I have to calculate what happens to the currents when I do this. Remember, the currents are defined by the formula that I also wrote down here. You have to take the trace of the Lie algebra generator, and that's the convention I'm picking, times d plus g, g to the minus 1, and similar for the other current. So let's work out what happens when I modify my solution in this manner. Okay, so what we do is we take a solution that was of the type G0, a periodic solution, or rather fixed by this fixed monodromy. And now we have to include this factor. So now what we want to calculate is that the JA of R is now K times the trace of TA. And now I'm writing out D plus of G of D of G. And so, okay, so this stuff doesn't not do, okay, so I'll write it as, let me write it, what happens. So I have to apply this to e to the I times W right over 2 x plus times sigma 2 times my old G right 0 of x plus. Then I have G left of x minus. And because I'm interested in the plus derivative, I don't have to write it out. And then I have here G inverse, which is GL x minus to the minus 1, G right 0, x plus to the minus 1. And then I have to write the inverse of that, e to the, a bit more blackboard space here, e to the minus IW over 2, x plus sigma 2. And I should write now W because W right is equal to W left is equal to W is an integer. Okay, so now I have to evaluate that. Now, obviously, you see the dx plus, I can stop the dx plus the action here because this doesn't depend on x plus. So this term obviously cancels against this term. That makes it already less to write. And now there are obviously two derivatives. The d plus can hit here. So what am I going to get? I'm going to get a term that looks like K trace TA. And now I'm going to get two terms. If the d plus hits here, I get an I times W over 2 times sigma 2, G0. And then the G0R will cancel against this G0R. So that's all there is. And the other term is plus, if the derivative hits here, then I get e to the I times w over 2 x plus times sigma 2 d plus of gr0 x plus times e to the minus I, sorry, times g0 r x plus to the minus 1. So this is this term times e to the minus I w over 2 x plus sigma 2. Right? And then, so that's what I have to calculate. Now, if you think about it, you see this is basically the old current, right? This is the original current. And it's now conjugated by that. But I can either think of this conjugating, or I can think of the conjugation conjugating the TA. So I can write this as k times trace of TA times IW2 over sigma 2 plus k times trace of e to the minus IW over 2 x plus sigma 2 times TA times e to the I times w over 2 x plus sigma 2 times, I just write it gr to the minus 1, the old thing, the one I had before. And now it depends a little bit on which component I'm looking at. So in the convention, so the conventions are, I mean, somebody should have worked a little bit better on these conventions, because they're the sigmas and then the t's. So the T3, to confuse absolutely everybody, and this has confused me for a long time, I misread the paper many times, is proportional to sigma 2. There you go. And then T plus and minus is proportional to sigma 3 plus and minus sigma 1. But that's what it is. The sigmas are the Pauli matrices, so everything is totally explicit. So now we can just work this out. So let's work this out for J3 of R. So when you pick TA to be T3, you see T3 is just equal to, by this funny convention, minus I over 2 sigma 2. Then you have a minus I over 2 times an I over 2 gives you plus 1 over 4. Sigma 2 squared has trace equal to 2. So this term just tells you this will be equal to k times w over 2 plus, so this comes from this term. And then from this term, if sigma 2, since T3 is also proportional to sigma 2, obviously sigma 2 commutes with itself. So this term goes away and you just keep the old current. So what you read off from that is that the 3 component of the current just gets shifted by a constant term. And what happens to the plus minus component of the current? Well, what you have to do for that is you have to ask, what is this for this being equal to plus minus? And that's a little calculation, which you probably better do in the privacy of your room than seeing me struggle on the blackboard. I mean, it's not the rocket science. I mean, e to the sigma 2 is an explicit matrix, so you can write e to the I sigma 2 as an explicit matrix. It's basically cosine, sine, sine, cosine, and then you just multiply this through. And what you find at the end of the day, and it's a very elementary calculation, but I'm not going to do it for you here, is that this is equal to e to the minus plus I times w times x plus times t plus minus. So the t plus minuses go back to themselves, but they pick up a phase e to the I, e to the minus plus I w x plus. So what this tells you is that j plus minus r, you see for them this term is 0 because the trace of sigma 2 with sigma plus minus is 0 because the traces of the different sigmas are 0. So this term is absent. And this term, you just pick up this phase, and then you have again the old current. So what you learn from that is that this is equal to e to the minus plus I w x plus times j plus minus r of x plus. That's what you calculate. So that's the sort of algebraic description of having introduced these additional solutions, right? I'm taking these additional solutions and I'm translating it, what it means from the point of view of the affine Kac-Moody symmetry, and that's what it means. Yes.
There is a bit of confusing point here for me, because you introduced this extra solution because you want to describe universal cover. But even if you want to describe just SL2R, you should include them, but
no, for
WR is not equal to WL, or not?
No, but I mean, if I'm looking at SL2R, then I have to be, then it has to be periodic in T, right? So you're saying it's also periodic in T?
Yes, you just need that WR minus WL is a multiple of 4 pi.
Well, or sorry, in this convention. Yeah, so you would have to use something like that. Yeah. Maybe you have to do this for SL2R as well. Yeah.
So it seems to me that going from SL2R to the universal cover is not adding new solution, but restricting.
Yeah, you're right. Well, I mean, but then that's not compatible with this, right? Are you saying WR minus WL has to be equal to a multiple of pi or 2 pi?
4 pi, maybe.
4 pi, whatever. Yeah, so maybe you're right. Maybe you're right. Maybe there's also additional solutions for, I think you're right. There's probably also additional solutions if I don't go to the universal cover. But if I go to the universal cover, I have this constraint on this class of additional solutions. And in fact, this is, I mean, you see for SU2, you may ask, why don't I have to do the same for SU2? And for SU2, if you were to do the same thing, you would actually land on the same spectrum. You're not introducing new degrees of freedom because, I mean, this will turn out to be spectral flow. And the spectral flow maps the SU2 representations, again, back to standard highest weight representations. So normally, you're probably right, one has to include these sectors as well. But for SL2R, they generate new representations, as I'm about to explain. And you're right, the universal cover is not responsible for adding new solutions. They're there anyway. It's more responsible for removing some.
Okay, thank you.
Yeah, you're right. Yeah. Okay, so let me explain to you what this means in terms of the affine Kac-Moody algebra. So remember, we have this mode expansion, JAR of X plus. I said you can write as a sum over JAN. And I think I forgot a minus sign here yesterday. There should be e to the minus in X plus. Otherwise, I'm going to run into trouble now. So that's the consistent solution with everything else I'm doing. So when you translate this, you see what this means is that J3, so J3n, the new J3n is the old J3n. And then the constant term means that the zero mode term gets shifted. So plus k times w over 2 delta n comma 0. And what you find for j plus minus n is that this is the old j0 plus minus, but now n gets shifted up and down in terms of w, because you see this factor basically just shifts the mode number, because I mean this just multiplies to the exponent and thereby you shift the mode number. And what you find is that this is the set of transformations you get. And what this means is the new solutions are described, you can think of them as being described on the Fock space of the old solutions, except that the SL2R now acts in a modified way. So you have the old Fock space on which the J0s act like they acted before, but now on the same Fock space, I define a new action where the new modes are defined in terms of the old modes plus corrections. And in fact, what you can check is that this is an automorphism of the affine Kac-Moody algebra associated to SL2R, i.e. these guys satisfy the same commutation relations as the original guys if we redefine them in that manner. So this is an automorphism, and whenever you have an automorphism and you have a representation, then the automorphism produces for you a new representation. Now, there's no guarantee that it's a genuine new representation. It may be the old representation in disguise, but at least potentially it's a new representation. Normally you would think it's a new representation. If the automorphism is outer, then generically you get a new representation. If the automorphism is inner, then you won't. Then you're just relabeling the states. Now, you can check that this is in general an outer automorphism. And the reason for that is you see that it shifts the mode number in this funny way. So if we start with the highest weight representation, and so on the highest weight representation, you remember we had J0 plus n on the state Jm is equal to 0 for n bigger than 0. That was what it meant to be a highest weight representation. But now, if I think about it in terms of the action of J plus n acts on these states. by saying that this is the same as J0 plus n minus W acting on these states. So this is only 0 if n is bigger than W. So what this means is that there are some negative J plus modes that will not annihilate the highest weight state. And as a consequence, it's not a highest weight representation. It's a representation where there are certain negative modes that you can apply as many times as you want, and they will always be non-trivial. And so these are generically not highest weight representations. You can also see it in terms of the Virasoro algebra. So if you look at it in terms of the, if you ask what does the Virasoro generators do under this modification? Now there is sort of an abstract way of doing this because you know the commutation relations of the Virasoro generator with the currents. I mean, you know that the Ln generators has to, with the JAM generators, have to satisfy this commutation relation. And then compatibility with this will tell you how L transforms. And what you find is that Lm transforms as Lm0 minus W times J03 M minus K over 4 times W squared delta M comma 0. This term you only see if you insist that they still satisfy Virasoro algebra. And this term you get by simply demanding that this is also an automorphism under this transformation. And you see, because of this term and the fact that the J30 spectrum is unbounded unbounded to the positive line, if I take W to be positive, then the zero mode of L0 will be unbounded. So these representations are not included in what I had before, because before I had a bounded L0 spectrum, because I had the highest weight state and the positive modes killed it, and L0 move you up. And now, once I've included the spectrally flowed sectors, I've genuinely produced new representation with an unbounded L0 spectrum. But this hinges on the fact that these representations are infinitely extended to the right, and therefore that this eigenvalue can become as negative as you want. In particular, if you think about doing the same thing for SU2, you see for SU2, you have finite dimensional highest weight representations. And what you find is that after you have applied this spectral flow to an SU2 representation, you just get another SU2 representation. And for SU2, what you find, I mean, for those people who are sort of familiar with this, sigma will map the Jth representation to the representation associated to K minus 2 over J. So it'll just flip around the, so it's order 2, so sigma squared will be trivial, will map a representation to itself. Sigma squared is inner, sigma is outer. And in fact, this has to do with the fact that SU2 is a double cover of SO3. And what this is really implementing is the quotient going down to SO3. But this is just as a side comment. But what's important here is that we genuinely get new representations. And therefore, this spectrum that I wrote down before was really too small because it didn't include any of these solutions. So I have to include my spectrum. And now the correct ansatz for what my Fox space of this worldsheet theory should be is that there should be a sum over these winding sectors, and I'll restrict myself secretly to W bigger than 0. Then I have this integral over J, or sum over J, and then I will have, and I write this like such. So by this, I mean the representation induced by this automorphism, sigma to the W, and I apply this simultaneously to left and right movers because W right times W left is equal to W. So this is basically the Maldacena or Gourvet spectrum. And as I explained to you, the spectrally flowed sectors come from the fact that you have to have these periodic solutions that are periodic in phi, but not periodic in T. Well, that you have these additional solutions because SL2R has these additional solutions, and then the fact that we are in the universal cover means that W right is equal to W left rather than the difference is something funny. Okay, so this is the spectrum we have to work with. And now the idea is that now we've identified this worldsheet spectrum. Now the aim of the game is that we are going to work out the physical states that satisfy the physical state condition. But before we do that, there is one more thing we have to do. Now I'm losing track of my notes. Oh, yeah. So far we have done everything bosonic. And bosonic is fine, but it captures the essence of the spectral flow. But in order to really get the symmetric orbifold, we have to deal with the superstring. So what's the superstring version? You see, so far I've really only concentrated on the ADS3 factor and only concentrated on the bosonic spectrum. Now I have to look at the superstring version. So what's the superstring version? Well, so the superstring version is actually relatively easy to describe. So what happens is, you see, we had this SL2R bosonic algebra level K. And if I'm looking, there's a natural supersymmetric generalization of it. And the natural supersymmetric generalization consists of writing an upper index and writing a 1. That means it's n equals to 1 superconformal. And what does this algebra consist of? Well, this algebra consists of the generators JAN that satisfy an SL2R level K affine Kac-Moody algebra with the commutators I wrote down before. But then in addition, you have fermions that also transform in the adjoint representation of SL2R. So there are 3 fermions, psi3 and psi plus minus. And so the J's with themselves give you an SL2R, and the J's with the psi's give you just they sit in the adjoint representation, so they just transform as somebody who sits in the adjoint representation. So I hope this is so these are the structure constants of SL2R. So 3 with plus gives you plus times plus, 3 with minus gives you minus times minus, and so on. So it's just they transform in the adjoint representation, and then the psi's by themselves just satisfy their free fermions. So the non-trivial anti-commutators they satisfy are of the form psi, and again there's a funny minus sign because we are in SL2R. So there's a minus. There's a k over. There's a k. There's a factor of k here, and there's a factor of minus k over 2 here. So going to the superstring, it basically means you replace the bosonic algebra SL2R by the sort of supersymmetrized version. And the way you think about it, this is like NSR normally functions. I mean, these are the bosonic degrees of freedom of your target space. And for each boson dx mu, you add the fermion psi mu. So the fermion has the same labels. It also sits in the adjoint representation. It transforms under the bosons in the adjoint representation. You can't really do anything but, and then it's a free fermion just because there's nothing else you can do. Okay, so that's basically the SUSY version for ADS3. So that's what you have to do for ADS3. And then you have to do the analogous thing for SU2. For SU2, you also enhance the SU2 level K prime affine Kac-Moody algebra by adding in fermions in the adjoint representation of SU2, and they satisfy the analogous commutation relations as that. And then the T4 is the T4. Now we want to, so the first thing I have to explain to you is why the level of the SL2R is quantized. I was asked this earlier. And the reason for that is that it must be equal to the level of the SU2. So let me explain how this comes about. Now, when you look at this super conformal, super affine algebras, you can ask yourself, what's the central charge? And the central charge, there's a clever way of calculating the central charge, and that's sometimes useful. You see, this is a coupled system. So, I mean, how do you calculate central charge? You try to separate it into blocks, and then you just add the pairwise commute with one another, and then you add the central charges of the blocks. Now, here you can't do that because the stupid fermions transform under the bosons. So you can't just say it's the bosons plus the fermions because they're not, you have to disentangle them. Now, in fact, you can disentangle them. And that's what goes under this decoupled current. So this is meant to be a different letter than this J. This is a more curly version of this letter J. And what you do is you define new generators, new currents, which are the old currents, and you correct them by terms that are bilinear in the fermions. And they look explicitly like that. So for J plus minus, you just do that. And then for J3, you take these J3s And then the way you decouple is that you add to it the term j minus j plus. I mean, these are to be understood as normal ordered products of this size. So what you do is you take your currents and you add to them suitable fermionic bilinear terms. And then what you can prove, and that's a little exercise, is that these currents then commute with the fermions. You basically remove the fermionic piece of the currents so that these guys commute with the fermions, and they still satisfy an SL2R affine Kac-Moody algebra, but their level has been shifted. So they now satisfy SL2R not at level k, but at level k plus 2. I mean, for people who know what's secretly happening here is that the free fermions themselves build an SL2R algebra at level 2, and you're basically sort of taking the coset. You're sort of taking them out, and then rather -2 taking them out, and then you get this term plus the decoupled fermions. But now it's very easy to calculate the central charge that comes from this factor. So when I calculate the central charge of ADS3, so you see for ADS3, I have this SL2R supersymmetrized level K. Then I have S3. Then I have SU2 supersymmetrized level K prime. And then I have a T4. So let's calculate the central charges. Well, so I have to calculate the central charge of this decoupled SL2R. Now, the central charge of a bosonic SL2R at level K is 3K into K minus 2. So now when I shift this, what I get is I get a 3K plus 2 over K. This comes from the decoupled SL2R currents because they're at level K plus 2. Then from the fermions, I get 3/2 because 3 free fermions give me 3/2. Each fermion contributes a half to the central charge. Then I do the same thing for SU2. So for SU2, what happens is for SU2 level 1, level K is the same as SU2 bosonic at level K minus 2 plus 3 fermions. So here for SU2 level K, the central charge is 3K minus, this is at K prime. So this will give me, so this is at K prime. So this will give me 3 times K prime minus 2 over K prime plus 3/2. And then the torus will give me 6 because the torus is 4 bosons, which gives me 4. And 4 fermions, each fermion gives a half. That's another 2. So altogether 6. And this has to be equal to 15. That's the critical dimension of superstring theory, right? I mean, the no-ghost theorem tells me that I have to live in the critical dimension. So that has to be equals to 15, which corresponds to a superconformal theory in 10 dimensions, 10 bosons and 10 times 5 fermion, 10 times fermion, 10 times a half fermions give you 15. And if you stare at this, you see you get a 3 from here, plus 6 over K, plus 3/2, plus 3 minus 6 over K prime, plus 3/2, plus 6. And now you see 3 plus 3/2 plus 3 plus 3/2 plus 6 is equal to 15. So therefore, what you learn is that 6 over K minus 6 over K prime has to be equal to 0. And therefore, you learn that K has to be equal to K prime. I mean, this is also familiar from a supergravity perspective. That's just saying that the radius of the ADS space has to be the same as the radius of the 3-sphere. That's the supersymmetric supergravity solution. But the CFT version of it is that in order to get a critical string theory, the level of the SU2 and the level of the SL2R have to be equal to one another. And therefore, because the SU2 level is quantized, the SL2 level has now also turned out to be quantized because they have to be equal to one another. There's a question?
So, sorry, I have a question on the shifting of the level. Maybe I'm confusing myself, but with the different conventions. But also in the bosonic WTW model, you have a shift of the level by the dual Coxeter number.
Well, that only appears in the central charge. The central charge formula of G level K is k times the dimension of G divided by k plus the dual Coxeter number. So that's, for example, for SU2 level k, this gives you 3 times k because the dimension of SU2 is 3, and it gives you k plus 2 because the dual Coxeter number of SU2
Yes,
is 2.
and if I'm not wrong, for SL2R there is a minus sign.
Yeah, so for the SL2I, exactly. For SL2I, basically, you can think of this as the dual Coxeter number being equal to minus 2.
So is it true that by adding fermions, I have an opposite shift?
Absolutely.
So,
yes.
okay,
So this is actually a very important point. So you notice here, you get a factor of 1 over k and 1 over k prime here. Whereas in the Bosoni case, you would have had a factor of 1 over k plus 2 and 1 over k prime minus 2 or whatever. Now, why is that important? Remember, k is the radius. So if you think about it, like you weren't smart and you took this Wessel-Witten model, you turned it into Feynman diagrams, and you would do a Feynman calculation, then the powers of 1 over k is basically the higher loop corrections as you would calculate it from a Feynman diagram. And then in the Bosoni case, you would have something like 1 over k plus the dual Coxeter number. And the way you think about it is that this is 1 over k times 1 plus h dual over k to the minus 1. So this is 1 over k times the sum from n is equal to 0 to infinity of h bar over k minus this to the power n, right? So what you would see is you get infinitely many corrections in perturbation theory if you treated this naively in perturbation theory. Now what happens in the SUSY theory, you see, the SUSY theory is sort of not renormalized, and that's manifesting itself that the central charge will involve just the unshifted level, and therefore it's one loop exact. You don't get any higher order correction to it. So that's the reason why this is exactly opposite. And that's a hint that SUSY is doing something good for you.
Okay, thank you.
Okay, so this is basically, so now we know that we have to live at the same level, and now we just have to put everything together and analyze the physical spectrum. Now I'm out of my many right. So now what we have to do is we have to. So let's write down the spectrum. And actually, so here there's some small subtlety. You see, I explained to you spectral flow on the level of the SL2R Wessel-Witten model, but now you're going to ask yourself, so should I spectrally flow the J's, or should I spectrally flow the curly J's? Right? I mean, they're both SL2R Wessel-Witten models, and I told you how to flow them. So which one should I flow? And the answer is it doesn't matter. So why does it not matter? Well, because you see, spectrally flowing the J's and spectrally flowing the curly J's differs by whether you spectrally flow the fermions or not. There's an analogous way in which you can spectrally flow the fermions. But for the fermions, if you spectrally flow them, you're just rearranging the states. You're not generating any new states in your Fock space. Just like with SU2 level k, where the spectral flow just maps the Jth representation into k over 2 minus j representation. With the fermions, it just reassembles the states. So whether you spectrally flow the fermions or not is up to you. You're not describing a different spectrum, you're just describing them slightly differently. And it's more convenient to actually spectrally flow the coupled SL2R generators, because the coupled SL2R generators are the geometric ones. Because geometrically, the fermions will also feel the Mobius symmetry. So they should also transform under, say, the zero mode. So decoupling the fermions is just a trick for the purpose of calculating the central charge. But the real SL2R is the coupled one, because the fermions, I mean, these are the tangent vectors, they live in the tangent space to the manifold, they also feel the rotation of SL2R, and to remove them would be artificial. So what we are going to do is we're going to spectrally flow also the fermions, i.e. we spectrally float the coupled generators rather than the decoupled generators. And what this means is that the K that will appear here is really the K I'm talking about here, rather than K minus 2 or K plus 2 for the case of SL2R and SU2. So I'm flowing the full generators. And then on this resulting Fock space, which will look, so there's the SL2 factor. So again, this will look like the sum over W, then I will have the sum over J, and then sigma to the W Hj. But now these are the super conformal representations, but that we are happy with. And then I have a similar factor for SU2. This is like the covariant description of string theory, right? This involves the time direction. ADS3 contains the time direction. So in order to describe the physical string states, I have to impose the physical state condition. So this will be the condition that GR of phi is equal to 0 for R bigger than 0. And I'm thinking of here working in the Navier-Schwarz sector. There's always a Navier-Schwarz sector and a Raman sector, but the Navier-Schwarz sector is the interesting one. And then you have Ln on phi minus a half times delta n comma 0 on phi is equal to 0 for n greater or equal than 0. So these are the physical state condition. This is just like if you open Green-Schwarz-Witten, you do a flat superstring. That's what you have to impose in covariant quantization, right? It's the usual n equals to 1 superconformal symmetry you have to impose. And in the Navier-Schwarz sector, the mass shell condition, L0 has to be equal to a half. That's the mass shell condition in order to get the no-ghost theorem going. So now what we have to do is we have to evaluate, we have to look for the states that satisfy these conditions. We have to enumerate all of them. And then we want to find out what their space-time charges are. And that will describe for us the space-time spectrum of this specific worldsheet theory. So the interesting condition here is that L0 has to be equal to a half. So what does this mean? Well, remember, we have to work with the real L0. And in the spectrally flowed representation, L0 gets shifted in that way. But what I'm going to do is I'm going to spectrally flow. So this is, I'm going to use exactly this formula. So the L0 condition will amount to the following. It will amount to the H0 of SL2R. So for my SUSY theory at level K, plus the H0 of the rest. So the rest will be SU2. So the rest is SU2 plus the torus. So this will be the ground state conformal dimension. Then there will be some excitation number. This is the total excitation number coming from everybody. And that has to be equal to a half, right? That's the mass shell condition that I will have to impose on this spectrum, right? You have the SL2 factor and the rest. The rest is SU2 and T4. This is the conformal dimension of the ground state of SL2. That's the conformal dimension of the ground state of SU2. That's the excitation number. And I'm thinking of looking at states that are in the vacuum of the T4. I could also include that. Doesn't really matter for the analysis, just to be simple. And this factor, for this factor, I now have to use the fact that this is spectrally flowed. So this will be the ground state energy before spectral flow. And the ground state energy before spectral flow is the Casimir. So this will be minus J into J minus 1 divided by K, right? Because in the SUSY theory, I get this shift. It's the Sugawara construction will have a level K down here for the same reason that we discussed before. And then it'll be minus W times M. So M, I will call the eigenvalue of J03 before I apply the spectral flow. So this is the eigenvalue of this guy. And then I have to subtract minus K over 4 times W squared. So that is what this term is. And then I have plus H0 rest plus N is equal to a half. So this is the mass shell condition I have to solve. And now I'm going to solve this mass shell condition for you and explain to you that we get something interesting. So let's just do this. This is maybe I can do this.
Yeah, perhaps you can take another 5 minutes. Is that enough?
It'll be 5 minutes. It's
Okay.
it's a very simple. I mean, it's very, very elementary, except it's quite key. So I would quite like to explain it today, and then we can discuss its consequences. So what I'm going to do, and at this stage, I'm just declaring this. So I'm going to set K is equal to 1. That I've told you before, that you are used to. And now I'm going to say that J is equal to a half times I times 0. So I'm going to look at a continuous, only continuous representations. I'm only going to look at the one for which P is equal to 0. Now the justification at this moment is non-existent, but I'll promise you next time I'll begin to explain to you that this is what you have to do if you look at it from the hybrid formalism. In this language, it's not obvious why these are the right representations to look at, but grant me, just look at these representations and see what happens. Okay, so what's the Casimir? Well, the Casimir is a quarter. So what does this equation become like? This becomes a quarter minus W times M minus a quarter times the W squared is plus H0, and I stop writing this rest stuff now, plus N is equal to a half. Okay, so now this equation I have to solve. And remember, in the continuous representation, the eigenvalues of J30 are up to me, because the continuous representations, remember, they are labeled by Cj alpha, and M has to be of the form alpha plus Z. But I can simply take this equation to solve for M and then declare that that means I'm looking at a representation with the corresponding value of alpha. And because all values of alpha appear inside this direct sum, so if I'm looking at a continuous representation, I would sum over all values of J and alpha, there will be one term in the sum where this mass shell condition will be satisfied. So I have in mind, I take a specific descendant and I ask for which term in this integral does it satisfy the mass shell condition? And I'm saying, okay, I'll just take this equation, I solve it for M, then M tells me which alpha, and that picks out the term in this integral where it matches the mass shell condition. Okay, so I solve this for M. Okay, that's not difficult. I just bring Wm to the other side. So what is this? Wm is then equal to minus a quarter, a half minus a quarter minus a half, minus a quarter W squared.
Matthias, sorry, just to say that the equation should be equal to 0, right? So
say again.
Equation equal to 0. So the equation misses equal to 0. I'm here.
It's equal to a half.
Ah, there is an equality sign.
I mean, this is in a Navier-Schwarz sector of a Ramond Navier-Schwarz sector string.
I thought it was a minus and the equal because I can't see from here. I'm sorry.
Sorry. No, this is equal to a half, and this a half. This is the usual a half ground state energy in the Navier-Schwarz. Yeah. Sorry. Okay, so this is the equation. Okay, but now remember that we are not interested in M. M is the J30 eigenvalue before spectral flow. And we are interested in the J30 eigenvalue after spectral flow, because that's the real J30, right? The other thing is just a way of describing these representations. So the real J30 eigenvalue, remember that J30 is equal to J030 plus KW over 2. And this eigenvalue is denoted by M. Remember, that was the term that appeared in the shift formula for the conformal dimension. So if I'm interested in this, and remember, this is the scaling dimension of the dual CFT. So this I can also call H, and think of it as the conformal dimension as looked at from the point of view of the space-time theory. So for that, I should not look at M, I should add to M K over W. Well, first of all, I should divide by W. So that's not hard. And then in order to find out the space-time conformal dimension of the corresponding state, what I have to do is I have to add KW over 2, which is just W over 2. But look, there's W over 2, and this term is minus W over 4. So what I'm going to get is W over 4 minus 1 over 4W, which comes from here, plus, and let's set H0 to 0 for simplicity, plus N over W. Now it depends whether you've seen the symmetric orbifold before or not. If you have seen the symmetric orbifold before, you should say, aha. If you haven't, you should not say anything. And from your reaction, I assume you haven't seen it before. So that's what I'll explain to you next time. But this is exactly the conformal dimension spectrum of a symmetric orbifold, where this is the Casimir energy of the ground state. And this is what you expect for the symmetric orbifold of T4. And the excitation numbers in the spectrally flow in the W cycle twisted sector, and I'll explain this next time, are not integer moded, they're fractionally 1 over W moded. So this exactly reproduces the spectrum of the symmetric orbifold. So obviously so what I'll explain to you next time is the other way of getting at this formula from the symmetric orbifold. And then I have to answer all the nasty little questions is, why was I allowed to do that? And what happens to all the other degrees of freedom and all the rest of it? And then the proper answer to that, I'll give you some hand-waving answer. And then the proper answer will be the hybrid description, where there's a very clean answer, where this comes out of the representation theory of the super Lie algebra, and where all the degrees of freedom do exactly the right thing to match then exactly the spectrum of the symmetric. But here you see the first sign that you're on the right track. This looks to somebody who's seen a symmetric orbifold spectrum before like the symmetric orbifold spectrum. So now you just have to dot the I's and cross the T's to make sure everything works out, and it does work out, but that requires a little bit more work. But since I'm over time, I'll stop here.
Let's thank Matthias. No time for questions. Let me also encourage questions from Zoom.